It's weird because when I was doing it, I made the effort of going, formal manner, because usually when I present, I don't like to. Usually when I present, I usually present to students, and I don't like to go with the formal attire. I like to go very,
Mhm.
very informal. So, because
It
a
shows
lot of
that
the
one.
times, yeah, and usually when talking about with students, they're very, very keen to provide that distance between, like an academic, a doctor, a scientist, which is in the stage, whatever. So I like to do it informal. But in that case, in that event, I made the effort of going formal,
And you ironed a
and
shirt.
I earned the shirt and everything. But the issue was that I forgot to comb my hair, so that happened. I hope
I
that
think our
doesn't.
audience is going to be very understanding. Hello to everyone out there.
Hi, everyone. Mm.
But I see
uh,
what you're doing. I get it. I get it now. Nice. Thank
yeah,
you. Also,
that's
thank
great.
you.
So, shall we start now? We could wait a few more minutes. I think there are maybe a few more people to join. It's your call, Shaylee. Whatever you think is a good time to start.
I think normally Danes are quite punctual, but we have quite a few international people joining us today.
Okay.
Um,
So,
I saw in the chat, Jonas, you have your hearing intact. Well, I'm not sure though. I mean, there's this thing happening now, so I'm guessing that in a couple of years, I'll need to shave off the whole thing.
well, this is called wisdom. This and gray hair. So
That's
you
great.
yeah.
but I think we should get started if you
Yeah,
don't mind.
we will start. I think people
You're
that
both
will
looking
join.
good, and
Yeah.
let me just introduce you before we
Okay.
kick off your
So
presentation. So thanks everyone for joining our Danish Sound Cluster webinar on robot audition. And we thought this would be a cool subject to look at because in Denmark we have a lot of people working with robotics and a lot of audio people, but we don't have a dedicated robot audition lab like where these guys are working. So that's why we decided to invite them. And we have François Grondin here, who's an assistant professor at the University of Sherbrooke. And we also have Caleb Rascon, who's a research associate at, I'm going to call it UNAM because I can't pronounce the Spanish, the full name, but the University of Mexico. And both of them are conducting research in robot audition and auditory scene analysis. So thank you so much for joining us, guys. And I will let you take it away with your presentation. If anyone has any questions, you can write them in the Q&A chat. Or if you just have like general feedback or comments, you can write in the regular chat. And we aren't so many here today, so you can also just raise your hand if you would like to ask something directly to one of our speakers. We're going to record this today, so we can share it afterwards on our website. And we're also going to send you the PDF of the presentation. So yeah, please do get involved in the chat. I hope you will get something out of this presentation today. Thanks for being here, guys.
thank you so much.
Right.
So yeah, so I think that's a very good introduction. Unless there's something more you want to add, Caleb, I think
Yeah,
we
we,
can
we, we were planning to do the whole thing that Shelley just did with this slide, so I'm guessing we can we
we
can
can move
continue
to
on with the
the
next one.
yeah,
Yeah,
that
go
was a
ahead, please.
perfect introduction.
Oh, okay.
So welcome everyone. Thank you for attending today. As you probably saw, this will be more or less formal. The goal is to give you a nice introduction of what we're both me and Caleb are doing, and hopefully get you interested in that area of research. So I've known Caleb for a while now. So there are, I would say, a few people working on that specific research topic, but not so many. So it's a small community. So I think the first step here is probably to define what exactly is robot audition, which can sound very broad. So there are obviously different definitions, but what we want to do mainly is allow machine to have similar hearing capability as we do have as humans, right? So it's to provide obviously robots, but also machine in general hearing capabilities. And as we will see in this presentation, there's a lot of things going on in real environments. And we call that environment where we have all sounds and different phenomena, the auditory scene. And we will see in the next slide what exactly we mean by that. So the auditory scene, as humans, we evolve in different environment, either indoor or outdoor, and there's a lot of things going on. And we just, most of the time, we don't really realize how good we are at understanding our audio environment. But in fact, one of the things we have is we are able to deal with many people speaking at the same time. So just think of a family dinner with cross conversation, people talking to each other, and you can still talk to someone, whereas other people are talking in different conversation. If someone calls your name, though, you're going to be able to pause and switch to that person to answer what was asked. So you have this multi conversation attention where you can also focus on one given speaker. And this is generally what we call the cocktail party effect. So for robots, we have to be able to deal with that same type of a scenario. So having different speakers, and the robot will have to pick one or many of them and be able to understand what is being said by that person. But again, there's not, so speakers, people talking in the room is something we have to deal with, but we also have many source of noise. So ambient noise is something we need to deal with. So it can be as simple as a fan noise, but you can have a TV set in the background or some music playing. All this noise adds up and has to be also filtered or addressed at least to be able to focus on what matters. And on robots, what we do, we sort of cheat a little bit. So humans have 2 ears. On robots, we can have more than 2 ears. We can add more microphones. So in this case, we have many microphones, that can be 4, 8, 16, whatever. Obviously, engineers like powers of 2. But basically, we use many microphones to enhance sound, and we use them as some sort of microphone arrays, so antenna to listen to a specific direction. And on robots, there's something else we need to deal with, is what we call ego noise. So as you know, robots are not just like passive mechanical structure, they are active. So they have to interact physically with their environment, which implies that you have many actuators in different joints, and these actuators are quite noisy. These are motors or any other type of technology, but most of the time it makes some noise. So the robot hears itself. So as it's moving its arm, it's going to perceive that sound, and you have to address that as well. You don't want to pay attention to your own noise. Or maybe you want to make sure that the motion is doing what it should do, but you have to consider that as well. And finally, most robots are indoor robots. That means we are operating in a closed environment with walls, ceiling, floor, and so we have reverberation. So the sound will also bounce on surfaces, and that makes the whole process even harder to deal with. So we can go on the next slide. So as I said, we call that the cocktail party effect, all those sounds from the environment. And there are many things we might want to do, but some of the, I would say, a mainstream task that we try to achieve is to localize sound. So to know where the sound comes from, to separate the sound, to listen to a specific sound, and to classify the sound, to know what class of sound is currently active. And so we can move on. So localization, what it is, basically, I said earlier that we have many microphones. So these microphones installed on the robot behave as an antenna. So there are 2 things. Sound travels at a constant speed in air. Well, speed might change slightly given the temperature and other factors, but mainly we know, most of the time we know the approximative speed. And also sometimes the sound, the amplitude of the sound will change with distance. So using the phase and level information, we can infer the direction of arrival of sound on a robot. And that's very useful because just think of a common situation where you interact with people and someone calls your name. The first thing you will do is turn in that direction to address visually that person. So we believe that robots should be able to do the same thing to at least provide a more familiar interaction with the human operator. And then the next step on the next slide, it's separation. As I mentioned, a lot of things are going on in the room. People are speaking. We have noise. So what we sort of perceive at the microphone level is a mixture of all these sounds combined together. So one of the things we want to do is to extract the sound of interest. To do different things could be, obviously the most common application is ASR, so speech recognition, but we can do also a lot of things with that signal that is enhanced. So the goal here is to be able to listen to specific sound and hopefully, if not eliminate, at least reduce the interfering noise that we don't want to deal with. And the next slide, so I talked about sound, speech recognition, but on a more general view, sound classification is very important. So speech is obviously one sound of interest, but in our environment, there's a lot of different noise or sounds that bring useful information. So you can think of a phone ringing, a doorbell, dog barking, obviously someone speaking. All these sound events need to be addressed properly by a machine. The same way, if you hear, for instance, glass breaking sound, you might stop what you're doing and just address this event because it's now the higher priority event that you need to address. So we try to also bring that capability to robots so that they don't just focus on speech, but they focus on all types of sound. So we can move on.
Right.
I will let Caleb continue.
So all of this that Francois was talking about was all nice and good, but how do we do that? That's the issue that we really need to embark on, and that's really what we're trying to achieve. And it has taken us a lot of years, and we're still not done. And now we're not talking about what Francois and I are doing, but also what the community is doing. And so something that we need to address in this part, which is probably something that you're already thinking, is like, well, this is audio signal processing. What is the difference between that and what you're talking about, robot audition? And there are certain aspects that make it not only more, in my opinion, and I think Francois as well, much more interesting, but I think it's much more applicable as well. First off, when we're talking about robot audition, we're talking about real-time audio analysis. We're not talking about doing something using recordings. We're grabbing something from the microphone, and from that information, we are providing that at least in an online manner, meaning maybe with a little bit of response time there, maybe 10 milliseconds, maybe a half a second, but we're still providing that in an online manner, maybe real time. So no peeking to the future to provide results. We only have right now and the past, basically, like we live right now. Also, another issue that we embark on is we were talking about dynamic environments. Francois talked about a little bit about that. But when we're talking about dynamic environments, we're talking about something that is usually always changing. We're talking about ever-changing noise. That noise that Francois was talking about, that's not only a fan that is coming down there. It may at one point be a door slamming, maybe a little dog barking, etc. So that noise that we're talking about is ever changing. It's not something that we can filter out using, something very, very static. That's something that you need to be adapting. That also comes with the ambient responses. Meaning, what we talk about ambient responses is that reverberation that Francois is talking about, that is also dependent on where the robot is located inside the environment. Meaning that if it's in a corner, that reverberation is going to be very different if it's in the middle of the room. And because that robot is mobile, that reverberation is also changing throughout that position of that robot. As well, we have all the sound sources that are in the environment, which are not static, right? They're moving around. And even if they're not, because the robot is also moving, the relative position of that sound source is also ever changing as well. So, and at the end, in this paradigm, we're all talking about ever changing speech and non-speech audio characteristics. What that means is that sometimes, for example, right now, something happened with my voice, and maybe that voice changed a little bit from one point to another. Maybe the dog is a little bit sick, and maybe its barks a little bit different from the other ones, etc. So when we're talking about a sound source, we're not talking about a sound source that has its speech characteristics completely static throughout whatever. Maybe they're talking differently, maybe they scream, maybe they have whatever. So there's always this changing. So as you can see, when you're talking about ever-changing or dynamic environments, we're talking about everything is changing in that environment from the point of view of the robot, or in the case of the machine that is interacting with that auditory scene. Like I said, also, what we're talking about as well, in François mentioned a little bit of that, is that when you're talking about the microphones, there isn't a position in which that microphone should be. It's like saying, like, oh, we obtained a very good results with this cube, with this cube of microphones. Like, yeah, but where are you going to position that cube inside in the robot? Well, no, usually when we're talking about a robot, you need to fit that microphone in the geometry of the body of the robot, so that it at least doesn't seem like a space alien. I mean, you need to put that around either the head or maybe around the body, et cetera, et cetera. So the geometry is limited to that, to the position of the body. We probably could put microphones around the room, but that will defeat the purpose of making the robot be more independent. And well, we put this in bold because something that Francois and I are very, very keen on is that we don't get to retrain our models. Once we put those models inside our robot and start working, maybe we can probably be refining that models throughout time, probably. But once we are using that model there is no point in which let's say that a user comes in to the auditory scene and presents itself to the robot, and you want to now identify that person and say Shelly comes into the room. Shelly starts talking to a robot, and the robot wants to now identify her by her voice. We cannot tell Shelly to provide us an hour of data to then spend another hour in training a model just for Shelly. I'm sorry, Shelly, but we cannot do that. Our users are very flimsy, and retraining takes time. And the 2 hours that we take from Shelly are 2 hours that we're not taking care of other users there. And users are very flimsy in that manner. So models need to be very robust or be in constant refinement, so that this is able to be carried out. So you can see that there's a lot of specifics that is not only just audio signal processing. Robot Audition needs to take care of all of this when we're talking about it. So how do we do it? How do we carry it out? Right now, we're going to be probably oversimplifying a lot of the things of the possible approaches that we can talk about here. And we're going to be classifying these approaches or types of algorithms in two big chunks of techniques. One we're calling our algorithmic methods or signal processing methods, and other that is model-based methods. Now, when we're talking about algorithmic methods, there's a lot of them out there, and they're very known. Once you delve in a little bit into audio signals, you probably have heard of some of these techniques. If not, don't worry. But like beamforming, common filtering, generalized localizations, music, etc., and feature extractions like Fourier transform and Wheel of transform, etc. So there's a lot of algorithms that are out there that are known, and you can actually see the code in which they were carried out, and you very explainable types of algorithms. Now, like everything, there's some pros and cons for these. And pros in this case are they're very flexible in the sense that you can probably change the code on how they are carried out and go on with your day. So they're very calibrated to meet the current needs. They're relatively low computational requirements, meaning they're very lightweight in comparison to other types of methods. They're, like I said, they're interpretable, meaning they're open box. You can see how the recipe goes on, and you can see how all the steps that are carried out, and maybe you can even change them if you want to. And most of these have their online versions or real-time versions to be carried out. So from this point now, you'll say, well, there you go, use those. What is the problem? Well, the problem is that they have relatively low performance. The amount of separation, the amount of localization, the performance of localization or classification, they're not as good as other methods that we're talking about. And usually they require multi-microphones. So maybe, although these may change between techniques, some techniques require less microphones than others, but it's very rare, for example, to use just one channel, to use just one microphone for these types of techniques. Usually you're trying to compare the information from one microphone to the other for then try to extract the information you're talking about, either localization or separation, et cetera, et cetera. Now, on the other side of this are, like I said before, is the model-based methods, in which you usually have data from which you can train a model, so that data and that model provides the information, meaning localization or separation or classification. Now, there are several variations to this, but the most well-regarded ones right now, without a doubt, are the end-to-end deep learning methods. Now, very common to the other side, they also have pros and cons. And it's interesting because the pros and cons that these have, and the reason why we chose these two groups is because they're literally, well, not literally, but very close to being the yin and yang between each other. Because almost all the cons that the algorithmic side has, these are pros to this group, and vice versa. Meaning they're very high performance. The amount of performance they have provided for the last maybe decade and a half have completely surpassed by several magnitudes of information here. So they're very, very, very potent there, and they can actually be used using one microphone. If you have the right amount of data and the right type of data, you're able to provide some information just using one microphone. Some of them have, well, a vast majority of them can do this. So basically the opposite of the algorithmic side. And like I said, all the pros from the algorithmic side are basically the cons from this. The model-based, especially the end-to-end deep learning, are very heavy. They require a high computational requirements. They're not interpretable at all, especially when talking about deep neural networks. I mean, you know that there's some weights that are being calculated there, but what does the output of the third layer mean? Is that the Fourier transform of the Wayliff transform of the compilation, or like what does that entail? And frankly, I think it still is an open question here of what that means inside the model. And if you want to change it, you cannot go in there and change a weight. I mean, you can, but you're really not knowing what you're doing here. So if you want to change something in there, you probably require to retrain the model completely, so that, or refine it so that there's something more close to your needs. And this is the bit that, at least for my point, is the bit that I'm not too sure of use, if it's that applicable to Robot Audition, is that they usually work with recordings. They're very few exceptions, but the vast majority of these models require, I'm sorry, they cannot work in real time or online data. You're required to provide some type of recording, and then they provide the results based on that recording. Now you can say, well, you can provide then maybe a second and provide like window of seconds. Like, yeah, but one of these issues is that these models require a big input to work with, so that they provide these high performances. So that's where we lie. Now, like I said, so I think we've talked a lot of what we're talking of what we need to do, but I don't know, Francois. I think it's time that we brag a little bit.
Yeah. So there are obviously, you sort of see that there are two trends right now, and we're trying to get the best of both sides to do something that works in real life. So this presentation, we will show some of the methods we designed the past few years, both at Université Sherbrooke and UNAM, and hopefully that will give you some feeling of what's going on in Robot Audition and what we're targeting. So let's start with the next slide. Lots of information on that slide,
Yeah.
but I'll try to be as clear as possible. So the first task we said we are interested in, one of the main tasks is localization. So how to tell where the sound comes from. So what we have done at Université Sherbrooke, we designed this framework, that we call ODAS. That was actually some of my PhD work a few years ago, which is available online. So it's open source. It's all coded in C language. Basically, what we do is we have, if you look at the bottom left, we have this microphone array. So we install microphone at different positions on the robot, and we tell the system where these microphones are installed. And what the system first does is it looks at every pair of microphones. So it connects every microphone with each other and create those pairs. And also consider the fact that if you look at the example at the bottom left, if you have like a cube and you have microphones all around the perimeter, some pairs might not be active simultaneously because the surface is basically blocking some of the direct path of propagation. So we keep only the relevant pairs where we are sure that there's a direct path of propagation. And what we basically do is we look at the time difference of arrival of sound between each microphone for each pair. And once we have that information, we create this kind of virtual sphere all around the microphone array, and each point on the sphere correspond to a potential direction of arrival. So for each potential candidate, we check, what if the sound was coming from that direction? Would we get the observation we have on each pair of microphone? And we get a score for that position. And we do that for the whole sphere. Now, obviously, if we want to have a high resolution, we need to have a lot of points. So we do that in two steps. We have what we call the coarse sphere. So basically, we have a few hundreds of points. We do a first scan, we find the best candidate, and then we refine around that point to improve the resolution. And so we do that a few times. We scan the sphere, we get some potential direction of arrival, but then this is still quite noisy because as people speak, they pause for half a second, say between words. We can have some, well, if we have competing sound sources, sometimes one source will be dominant over the other one and so on. So we need some way to track a speaker over time to make it for those little glitches, if you want, or noise that we observe. So for that purpose, we use Kalman filters, and we sort of model the motion of the speaker around the robot. So we know that someone cannot suddenly go from one side of the room to the other side of the room. It has to be done smoothly because as the speakers, we move quite slowly. So we use a Kalman filter to model that smooth transition. And in that, using that, we're able to do some nice tracking and also deal with pause during the speech. When someone stops talking for a few seconds, then we can just what we call kill the source, or just stop tracking that person and assume that the person is done speaking. So that provides us with some sort of real-time tracking of different sound source. And as you see we have some interface we can use, and we basically see source appearing and disappearing around the robot. And at this point, we're mainly looking at the audio energy. So we're not only tracking sound, which are speech signals. It can also be sound event of any type. As long as the sound comes from a specific direction, we can track it and detect it. So that's what we do for localization. And this thing works with we've done tests with up to 16 microphones on a Raspberry Pi. So it's quite lightweight for many microphones, but Caleb will show you another system that's even faster for localization, which he worked on.
Yeah, but it's weird because a lot of people when we talk about the amount of resources that we have over here in Mexico in terms of well, in research or whatever, every time that I talk about this method, they were like, "Wow, so what brought you to the point of using only 3 microphones to do all of that?" And usually I bring up something the first time that I talked with Francois. I think I thought like, "Oh yeah, because it's a very good challenge to only use a small amount of microphones." And to be clear, it's because I only had 3 microphones at that moment. So I thought, okay, so what can I do with these 3 microphones? And surprisingly a lot. One of the things that we use is that we limited our scope of what type of sound sources we were talking about and we were using. And it's not a power of 2. Thank you, Giannis. That's a very good point. Is that we were just going to do speech signals. Others can talk with a lot of other types of sound sources, but once we provided just for speech signals, we found out 2 things. First off, we can then just work with a very small part of the electromagnetic spectrum in a frequency range that is not, the 24 kilohertz or the 48 kilohertz. It's just between 400 and 4 kilohertz around that area, which means that there's a small amount of data that we can use. And second, and as you can see in the first source 1 and source 2, there is that when we're talking about multiple speech signals occurring at the same time, is that speech usually doesn't overlap with each other. Yes, there are sometimes if Francois and I talked right now over each other, yes, you might just maybe see, look, there's a lot of overlap. But once you get to the nitty gritty, just you get to the 100 millisecond or 25 milliseconds windows, there's a lot of bits there that don't overlap. And it's in those little windows that we can then use this technique in which, again, like I said, is only 3 microphones, which means we only have 3 pairs of microphones to work with. And then we just use a very basic generalized cross correlation to find out the difference of time of arrival. But in this case, it's very, very similar to what Francois is doing. Now here the difference is that we use the different types of arrival between pairs to say, do they make sense? Are these times of arrival pointing at one direction and only one direction? And if so, it means that they are coherent, or that's something that a word that we liked at that moment is like, there is a coherence here, meaning that there is only pointing towards one sound source. If they are incoherent, meaning that one pair points to one side and maybe another pair points to another, it means that they're incoherent, which means that they probably at that moment 2 or more speech signals are active at that same time. So we need to just ignore it. Yeah, I know. I know we would like to use a lot of information here, but what this coherence check does is that once we get to the next step, this brief amount of time will provide a candidate very similar to what Francois is doing. It's like, oh, there's a potential DOA right there. There's a potential sound source right there. And throughout time, we just beginning to recollect those potential DOAs the potential DOA that we are finding in the environment. And then we use a k-means clustering, which is basically saying like, oh, we have a new potential DOA. We have something in this side. We have another in this side. Which one does it belong to? And like, oh, it belongs to this one because it's closer to this this side to the other, or it's another cluster completely. It's another cluster that is a new source that is now started talking. We put a Kalman filter just in case that cluster starts to move, and that's the submission results. Now, the interesting thing about this is that, again, we're just using 3 microphones. And one of the things that the algorithm side of things have is that they usually have this rule of thumb in which you can only be localizing as much as much sounds that you have meaning, I'm sorry, as much microphones that you have. Meaning, if you have 3 microphones, you're probably only going to be localizing 2 or 3 sound sources at the same time. It's meaning that's the reason why a lot of people use like for example, like 8 or 16 microphones, because the more microphones you use, the more source sources you're able to localize. This is an oversimplification, to be fair, but that's more or less the rule of thumb that we're talking about. In this case, there's no such thing with that, with the limitation. We were able to obtain and localize more sound sources than microphones that we had, and even though they were mobile. So that's one of the nice things about this. Now we're talking now about localization. I want to remind you that there are big three tags. Wow, that's a tongue twister right there. Big 3 tasks, which is localization, separation, and classification. So right now we're now going to be talking about what we do in terms of separation in the University of Sherbrooke and Yunnan.
Yes, thanks. That was indeed a tongue twister. One of the first thing we like to do, as I said, is we localize sound. So is there a sound of interest in that direction? Once we have that sound of interest, we know where it comes from. We would like to listen to it, right? To listen only to that one and reduce the interference from the competing sounds. Some of you probably know, obviously, about the well-known delay and sum beamformers, who just realign the signal and do some constructive interference and listen that direction. But delay and sum is not that great. I mean, it's easy, it's simple, but it doesn't perform so well. Some other beamformers do much better, such as MVDR or GEV beamforming. Now, recently, people have used time frequency mask to estimate the region where the sound of interest is active, and then estimate what we call the spatial covariance matrices to get the statistics, the spatial statistics, and use that to feed it to the MVDR or GEV beamforming. I will not get into too many details here. I want to focus mainly on the strategy here, but what you have to keep in mind is that somehow you need to produce that mask that will tell you exactly when your target speech is active. When you have only one speech source and the rest is noise, it's rather easy to use a neural network that you train, because you can tell the difference between speech and noise, mainly based on the structure, frequency structure, the harmonics, and the way the signal is organized. When you have many people talking, how can you know exactly which one you want to listen to? Localization gives us a cue here. We know the direction of arrival of sound, and we assume in that scenario that sources are not at the same direction. So you have, say, different people speaking, and you want to listen to one of them, which is at a unique angle. So we said previously that deep learning is not always the good choice. And one of the issue is that if we were to use many microphones and do beamforming with deep learning, we would have to retrain all the time for different geometries. So Caleb mentioned that as you position microphones on the, say, the robot torso or the head, you have to adjust to the shape of your given robot. And maybe you don't want to retrain with hundreds of hours of a speech for that specific geometry, because it becomes very impractical if you have to adapt the system to a new robot. So what we did here instead is we said, okay, we're just going to train for a given pair of microphones. So we're going to take 2 microphones and we're going to move them apart at different distances. And then once we have a model that can deal with this pair of microphone, we can sort of build a complete geometry with many microphones by addressing each pair individually, because we have a model that works for a pair of microphones. So we can just repeat that model for different pairs. And what we do basically is, in this example here in the figure, we have, say, 4 microphones, and we have a target source and an interfering source. So what you see here are spectrograms. So the x-axis is the time dimension, and the y-axis is the frequency dimension. So I always tell my students to label their plots, and I'm not doing it. But that's the what you see here. And the goal is, if you look at that array, in this case, it's a 4 microphone array. We can count 6 pairs of microphones. So if you look at the center part of the figure, you see the red lines define each pair of microphone. Now, the thing is, suppose you have the sound coming from the bottom of the array and the interference from the top of the array. When you look at 2 microphones side by side, like the first pair, there's no way you can tell which one is the target and the interfering source, because the way they are positioned with respect to the position of the microphones, you have this ambiguity of TDOA. They will both have the same time difference of arrival because both microphones are equally at equal distance of each source. However, when you look at the other pairs, for instance, the second one, the vertical one, if the sound comes from the top, the first microphone on top will capture the sound first, and the second one on the bottom will capture the sound second. Whereas if the sound comes from the bottom, it's going to be the opposite way. So the phase information here will give us some cues about the sound source of interest. So the goal here is that we tell the network, we tell the system what's the direction of the target source, and the system will use that training on that model, that deep learning network we train on each pair of microphone to produce a mask that will hopefully extract some of the time frequency features that only relate to that target source. So in that example here, we have 6 pair of microphones, and we can see that 4 of them are quite discriminative. We see that the generated mask, we have some yellow region, but a lot of bluish region, whereas 2 of them are kind of the combination of both speech and target and interference speech, because we cannot tell which one is the good one. However, once we average all of them, we get a target mask and a noise mask, and we see that the target mask, we have some in between values, but we still have those values that matters that really identify the speech that we care about. And we then use this mask to generate the spatial covariance matrices, and we use that with, in this case, GEV band beamformer, it could be MVDR, and we get the separated source. So I will not obviously go into details here, but the goal is that the point here is that we can use a network that has been trained on pairs of microphone and generalize to any shape of microphone array. In this case, we use a bidirectional long short-term memory network. I know this is not real time because we need to have some buffering, but this was just to prove to show the possibility of using a pairwise approach. Now, I'm currently working on some research to see if we can have something with a unidirectional LSTM. So basically, it's a fully causal system. We don't have to buffer to look ahead in the future. And if it works, hopefully it will, then we can do some enhancement regardless of the microphone array geometry. So we don't have to retrain all the time. We just use that pairwise model on different robots. And this was published in Interspeech almost 2 years ago. Yeah. So, and I will also let Caleb explain some of his approach as well.
Right. It's interesting every time that Francois talks about his methods, because it amazes me how we more or less reach our techniques in a very independent manner, and more or less in the same vein. While Francois is using a neural network to then estimate a mask and then feed it into an algorithmic one, my approach is more or less the opposite. I feed the whole microphone, whatever, into a beamformer, into an algorithmic type deal, and then that output I feed it into a neural network. Now, the interesting part of doing this is that this algorithmic side, we call it the phase-based frequency masking, which is more or less a beamformer here. So what we do is once we know what is the direction of our zone of interest, what we do is to align everything such that everything that comes, we align all the microphones such that everything that comes from that direction of interest is aligned, meaning we can probably do a delay and sum here, meaning that if we then sum it up, we have a constrictive interference there. But we don't do that now. What we do is that once we know that they're aligned, we go into the frequency domain and we inspect the phases. And we calculate the differences of phases from each frequency. And if the differences of phases are not above a certain threshold, then that means that that frequency specifically is aligned towards that direction, meaning that that frequency belongs to our source of interest. Now, it's a very, very simple beamforming type of frequency masking there, but what we obtain from this is that we can probably then have a binary masking here, meaning that we have a masking for a preliminary estimation of that sounds of interest, but we also have the opposite. We also have a preliminary estimation of the interference or the cumulative interference in the environment. And those two are then what we then provide to the BLSTM. The reason why we went for the BLSTM in our case instead of just the unidirectional one, even though we are also buffering a little bit, but still we obtain a half a second of response time, which is not that bad considering if we're using for something like a robot audition type deal. I mean, we can probably use that in terms. Maybe we cannot use it here in a Zoom call, because you will be seeing my mouth move, and half a second later you will hear something different. But something for robot audition may be quite applicable here. But what we then find out is that because the BLSTM is only being trained with the outputs of this algorithm, with this phase frequency masking, means that doesn't matter what geometry we are dealing with. If we change the position of microphones, we only need to compensate that in the algorithm, not on the network. Meaning that the network only needs to be trained with these two guys, and have provided very, very good results. The only issue that we have with this guy is that we've only tested it with simulated signals here, so no noise and reverberation still. So that is something where we really need to work on here. But what we also find out is, well, just with simulated signals in the state of the art, meaning these big models that are trying to use, several seconds of information and all of that, we were basically getting into a little bit of some decibels below the state of the art, but we were only using like 10% of the memory requirements. So that's what we're. So I mean, that's the big deal for this one. It's not, oh, it's having really, really good performance. We already have that. Like we mentioned, end-to-end deep learning have very, very good performance. We don't want to beat that. What we want to do is to use a very small amount of requirements. And you might be asking, well, you're using a BLSTM. That's a neural network. You could probably use a deep neural network there. How come you're using so little time, so little requirements here? Is that, well, even though the architecture is provided as, or is known as, a deep neural network, what we're doing is a BLSTM only with we're only using three layers there, because we don't need it to be so complex now. Since we're not feeding the microphones directly to the network, it is not working from scratch. And that's one of the big reasons many of these networks need to be so big, because they need to be that complex to obtain all the information that you want from there. But since we already are providing, this is more or less what we want, this is more or less what we don't want. So please work with this to just cancel each other out. So the problem has been reduced and have been simplified greatly, such that this little network at the end doesn't require to be so big, so that it can solve the issue that we're talking about. As a reminder, again, we're talking about localization, separation, and the third task here is classification. So now it's turn for Francois to talk about his works in classification.
Yeah, so thanks, Caleb. This is part of the work I've done. So recently I did some other, when I was doing my postdoc, we did some very nice classification with a huge amount of data on audio set and using your residual neural network. And we had very good results, but as you might know, this was super expensive in terms of data and computing power. So back in the days when I was young, when I was doing my PhD, I had this idea of doing some features engineering based on my understanding of pitch. So pitch is when you speak, it's the voiced part of speech. So any vowel, for instance, a, e, I, o, u, these are voice signal, and the pitch here provides some information that you, well, if you're singing, for instance, your pitch will change, but as you speak, your pitch will fluctuate over time. And that's interesting because speech is usually a three-mast ship. So when you had some noise, the first thing you lose is the fricative, and then you lose the formant, and finally you lose the pitch. So the pitch is probably the most robust feature that you have in noisy condition. And when you speak, your pitch will slightly change over time. So it will not be perfectly constant. It will not be, random. It will slowly change. So based on that, I designed some pitch extraction features. And I realized that, for instance, for on-voice speech, there's really no pitch of interest. There's no pitch. So when you apply that feature extraction, you get some random values. When you do apply it to voice speech, then you see that it, like I said, it changes very slowly. And if you have a musical note, unless it's a solo with a guitar solo, most of the time the pitch will be very, very static. So we use that information to extract some features. So based on the value of the pitch, the speed of change of the pitch, and we create some features, and we tested it on the different noisy environment that we see on the right. And what we see is that if you look at typical noise, you see that the pitch feature, we have a few, I'm not going into details, but we extract some information, and you see that most of the energy of the distribution is on the left. And as you add some noise, additional noise to that environmental sounds, you also get the same, pretty much the same distribution. Whereas when you have speech, either in clean or noisy conditions, the distribution of the features is in the same region. So basically, based on that, you can just draw a line and say, okay, everything on the left is non-speech, everything on the right is speech. So we designed this very simple classification method, and surprisingly, it works quite well. It's not as good as a deep learning network with 1 billion parameters, but it runs on very cheap microcontrollers and can do a decent job at distinguishing speech from non-speech signal. So then that means your robot can tell if someone is speaking in the room, or if it's just a phone ringing or something else that might be might require a different intervention or attention. So that's what we did. One of the things we did for classification, but I thought this was kind of interesting because it shows never underestimate the power of engineering features. It can be very useful to make your problems simpler in some cases. And I will let Caleb and then move on to the next slide with his work.
Right. Thank you. From our side, one of the issues that we have with classification is specifically when talking about, I mean, and I'm talking not only with deep neural networks, I'm talking about classification in general, is that the model requires to know the amount of classes to identify. And if we're talking about identify the person, let's say we build a model so that it can identify between Caleb, Chelly, and Francois. Yeah, but what happens when Giannis comes into the picture and we also want to identify him or her? I'm not sure of them. Let's call him. we will need to then ask Ioannis, oh, can you provide us like 2 hours of information for you, because we want to append that with that model, and give us like a 2 or 3 days so we can retrain this thing again. So that in practical terms is very very not practical basically. So what we do then is that instead of building a model that classifies just from the input, just from its sole input, what we provided then is say, what if we build a model that it doesn't learn the name of Caleb, Shelley, or Francois, but it learns if the two inputs, if the two recordings that is being inputted or that is being fed belong to the same person or not. So this model does not classify. This model is only achieving similarity between them. And that bit opens up a big special or a big opportunity here, because what we then have is that if we're able to do this, what we then only need to do is to obtain recordings of the persons that we already know, meaning Caleb, Shelley, and Francois. And once we have another recording that we need to identify, we just compare it using this model to those recordings that we already have. And based on a threshold saying like, oh, of all the comparisons, the one that is most that is the most has the most similarity is for Shelley. Okay, so that person that just talked is Shelley. But if Ioannis comes in and none of the comparisons are above a certain threshold, we can then say, first off, we don't know that person. Something that to be fair, are the models or classical models of classification can do, because they're always trying to see which one of those three persons is the most, and that's it. But with this thresholding type of similarity thresholding type of approach, we're able to say we don't know that person, and if we want to know them, that recording that Ioannis has just provided us, we just add it into the database of known recordings, and that's it. We now know Ioannis from that point on. Now, to do this similarity type deal and be it robust, what we used was a BLSTM as well, but only to encode that that recording or that input into what we call an embedding space. This is a series of numbers, of a vector of numbers that is representative of that person, right? So if that series of numbers is like the signature of this person, and we have another recording that provides a very similar series of numbers, then we know, oh, that person is certain, it's either Shelley or Francois or whatever. And if we provide another a recording or an input that provides a series of numbers that is not similar to the ones that we already have in our user database, then we know that they're not. And the reason why we go for the embedding is that, first off, it's a very small amount of numbers compared to the tens of thousands of data points that we obtain, even with a couple of seconds of information. But also, is very robust against either noise and reverberation, because it only is encoding the piece of speech that we're trying to do. So although we're trying to say here that we want to do something that is very lightweight and everything, we did spend a lot of time modeling this or training this model. However, the model already trained is very lightweight. You can run it in a CPU. So the training part we struggled with, but now that it's trained, you can carry it out, and you can find the train weights in that GitHub link that is below. Right. So what is we trying to do here? I mean, good for you. You're doing localization, you're doing separation, you're doing classification, and all of that. But what is the long-term goal here? And we mentioned in the beginning of that we want to emulate these hearing capabilities in a non-human entity, but we want those capabilities to be close to human hearing. And many of you will say like, "Whoa, that's a big goal here." I mean, to make any machine do something as well as humans is quite a big and long, really long term goal. So and maybe not even possible in some certain. So let's bring it down a notch and just call it that what we really want is to effectively analyze the auditory scene for the benefit of our day-to-day. Meaning, let's say we're talking about these Google Homes and Alexas, for example, maybe, or these guys over here, or maybe, just maybe, a lot of other bits, other types of applications that Francois is going to talk later on. But what this implies then is that the current state of the art provides very impressive results, but they're not built to run real time. They require an enormous amount of data and computational requirements, and a considerable amount of high grade hardware to be trained effectively. I mean, every time that I see a new paper that comes in and say like, oh, we now achieved a 99.5% performance, the first thing that comes to mind for me is like, what do I need to run that model? And if I need to run, these two NVIDIA Teslas in my computer to run it, I'm sorry, but for me, I can't use it. I don't see a reason to use that model because it's not applicable to I cannot run that in a Google Home. I cannot run it in a Raspberry Pi or in Alexa. I probably may be able to send into the model into another central server, but that opens up a whole bunch of privacy concerns and maybe lags there that I don't want. So what this goal implies here is that we want to develop techniques that provide comparable results, maybe not beat them, but comparable results, but they're actually usable. Now, usable in terms of being able to be run in modest hardware. And the reason why we want this is, and Francois is gonna talk about this, is that, think of the possibilities.
Yeah. So thanks, Caleb. And yeah, exactly. So if you're able to run those algorithms on low-cost hardware, you can do a lot of things. For instance, just think of the hearing aid research. Like when you have a hearing aid, you need something very small, low power consumption. You cannot carry a computer in your backpack. You have to have something very, very portable. So these algorithms need to be lightweight. Bioacoustics kind of connect with that as well. Any urban sound design, if you are doing, for instance, you're using drones for search and rescue, the drone is mainly offline. I mean, you deploy a drone in somewhere where there was a catastrophe, so you don't expect the internet, Wi-Fi, or the 5G to be operational in that region. So you need the robot to be able to proceed to perform analysis of the sound in a real-time manner without sending the audio to a cloud. And even smart home assistant. So Caleb raised the privacy issues. I mean, many people don't want to have a microphone, a tap in their house, just recording everything they say and send it to the cloud. But also, if you think about it a bit further, there's some environmental issue. Think like how much energy it takes to send some streaming to a data center, do some computation, and send back the result. Imagine that all those, you have millions of Google Home in the world, and say you reduce by 20% the power consumption on those devices. Well, it's 20% times millions of devices. So there's something here to be to care about. We have to be able to reduce the power consumption, to reduce the dependency on a connection to the internet. And these are all things that when we work with robots, we have to deal with these limitation. So it's a great exercise to try to achieve robot audition because it provides solutions for these applications that are very actual. It's not something futuristic, it's something we use right now. And if we go to the last slide. So we talk about robot audition. I hope that you can now appreciate what we're trying to achieve. We have those challenges we're trying to overcome that are very specific to robots. And again, as I said, once we have solutions for robots, we can also use them for a broad range of applications. Deep learning has been really impressive for the last decade, shown a tremendous improvement in terms of performance. But when it comes to using those large networks, it's not so trivial. So we believe that the solution somehow lies in between. It's not purely algorithmic, not purely deep learning. There's probably a sweet spot where we can combine both and get good performances in real time. And yeah, so that's what we've been doing for a while now, and we're still working on it. I don't think I think this is the beginning of a lot more research in that area. I think we just scratched the surface. So hopefully we will keep applying some of these methods to real life scenarios, and we get something that is more usable. So we've talked a lot. This is what happens when you like what you do. But we will have some time now to answer questions. I think we have till 10:30, Shelley, if I'm right. So please, it's now your turn to speak.
That is correct. We have a bit more time if we need it. Yeah, thank you so much. That was a great presentation. It's really a pleasure to have educators on the webinar. You are great communicators. Okay, so let's take the first one from Johannes. Can we introduce a microphone geometry invariant embedding so that we can discard the geometry information?
I believe so. I mean, that's one way of doing it. The issue here is if that embedding, again, there's going to be a lot of techniques that you can use here. I mean, we don't want to be throwing dirt of everything out there, but right now, what we need to be pondering is not if it's effective or not. It probably will. The issue here is how much resources would it be able to obtain such that it is able to be invariant towards the microphone geometry. How much data would you need to provide it such that the embedding is robust against that? And that's our issue here. And again, if we're able to train that and it's able to be run in a very low with very low requirements, it's definitely something that you can use. But again, you're using it to discard the geometry information. And right now, the issue here is that what other techniques there that are easier and more lightweight can you use to be robust against that? So we need to be using the appropriate techniques for the appropriate process here. And even though I don't want to throw dirt at those types of embeddings, I mean, I just provided embeddings for person identification. We do need to say, like, are we using those embeddings for the right task? And in my opinion, is that if you want to use embeddings to discard the geometry information, there are other types of techniques that are much more direct to be using for that instead of an embedding there. Again, but if you can prove me wrong, and you can say, look, this is very easy to train, this is very easy to run, and if that's the case, go for it. But for now, I'm not too sure that's the appropriate way if you want to reduce the computational load there.
And maybe I can add something to
Yep.
complete your answer, Caleb. I think it's a good point, the good question and good answer. And also something that is interesting is, well, as you've seen, I like to break down the problem as pairs of microphone. And one of the nice thing about that is that you can dynamically drop pairs of microphone if you need to. So depending on, as you know, on a robot, you have different processes running at the same time. Sometimes you might have some vision algorithm running that are very greedy, and maybe you just want to you have 8 microphones and you just want to use 4 of them, right? Because that's all the processing power you have at that moment. So I like the fact that if you don't depend on them, if you don't have this model trained for full matrix, you can just change the number of inputs, the number of pair of microphones, and drop some of them at some point. and you reduce your computing needs. And at the same time, if you, for instance, you have a faulty microphone and you can see that it is faulty because it's always noisy and it's not related to the other sensors, you can also just drop it,
Yeah.
right? So
Yeah.
that also makes the whole thing more robust, in my opinion. Yeah.
Just quickly, just to follow up, they mentioned something about what orders of magnitude of computational resources are we talking about. That really depends on the application, but usually when we're talking about like a Raspberry Pi, I mean, we're talking about several hundred megs of RAM and just a couple of cores that you can probably use in there. Now that's it if you're using a Raspberry Pi. But once you get to, I don't know, a hearing aid, I mean, we're talking about a small amount, maybe kilobytes of cache there, and so that bit is where it will depend on the application. But what we're trying to do is, like, for example, my first threshold there is like a laptop, a modest laptop. Let's start with that. And if it can run, and I'm talking a modest laptop without an integrated, without a discrete graphics card, maybe with Intel iCore, with Intel Core of i5 for the last 5 years, for example. And that's where more or less, that's like the upper threshold for me. Because if it doesn't run on that, I mean, it will limit a lot of your applicability. Into the rest, exactly. I don't know if we can bring in the next question. Tony. I'm gonna call it as we do it here in Mexico, Tony Torras Rosell. I'm not sure if that's the way you call it here, but that's the way that we're gonna go it.
You're welcome to read it. Yeah, and answer yourself.
I can. They say that I can see the importance of becoming independent of the array geometry, but how critical is the quality of the microphones for improving output of your element? That's a really good question. I'll tell you a little secret. Francois is from a lab that provided a fantastic audio interface, external audio interface called 8 Sounds USB. And it's fantastic because you just hook it up directly to your USB, and you had 8 channels to work with. Which by then, I think right now, using 8 microphones requires a interface that requires outside power and all of that, which was great. However, the microphones that they were using, my God, I mean, they were good, but you needed to, they weren't as sensitive. So when you needed to crank up the volume, unfortunately, when you crank up the volume, you're not only increasing the energy and the magnitude of your sounds of interest, you're also increasing the amount of noise that you're receiving. So yeah, you need to provide good microphones, but it comes back to the issue because a lot of the microphones that are good quality are big. I mean, I was using for one of my first projects a microphone that was more or less this size. That the whole pack was this size. I mean, you cannot tell a person that's using a hearing aid to plaster their head with 8 microphones of those things. So that's usually the back and forth that you need. Yes, the better the microphone, the higher the quality of your microphone, the better. Unfortunately, when you're talking about space, is even more so when you're talking about Robot Audition or the issue of hearing aids. That's a balance you need to strike. Fortunately, very lately, the microphones that your mobile phones are using are called MEMS microphones, which are very, very tiny, are very small amount, and they have been increasing in quality. So I think from that size, go with your MEMS microphones. They're already being used a lot, and stick with those. Just use the higher quality, the better, and go for that. But I mean, don't blow your bank account for that. But just try to at least obtain a good amount of quality. I don't know, Francois, you want to talk about a little bit.
Yeah, I mean, as long as so far we've achieved rather good performance with the cheap MEMS microphone. As long as Caleb said, they're sensitive enough. But nowadays you can buy those very small mics, and it's amazing. You don't need those big guy anymore. But now we use it's a few bucks per microphone. It's really not that expensive. What is costly is to do the PCB and the whole thing with the codec to do acquisition. But now we can deal with very low cost microphones. Yeah.
Right.
We have a
There's something.
question.
Oh, go ahead.
We have a question from Siba,
Yeah.
who would just like
hello,
to
are
ask you
you-
directly. Yeah.
Yes,
Hi.
can you hear me now? Perfect. Thanks
Yeah.
a lot. So it's more like a general comment question, and I would like to answer to have your thoughts about. So first of all, thanks for your presentation. That was awesome, and I really enjoyed it. So a lot of things rings to me when you were saying and commenting a lot of stuff in there. Like one is the 3 microphone issue. I'm from Argentina. I study acoustic there, and I say this is what we have, and this is what that's it.
Yeah.
And now I'm actually at the University of Miami doing like a more fancy stuff. And now I see the difference. So I have the chance to do a more sophisticated stuff, but I always have this be mindful of, well, the lower the better, right? Not only because of the amount of money you have to spend on that, but also resources and all the stuff you comment. But now I'm specifically working on hearing devices and hearing devices in general, like from cochlear implants to hearing aids to a lot of stuff in there, and actually very oriented to spatial hearing in general and multi-sensor integration. So a lot of things are like, now and I want to hear your thought about a particular topic. So I'm realizing that I'm doing a lot more of robotic audition that I thought while hearing you, but now like all these devices on hearing devices are getting more and more signal processing in there, a lot of more processing stuff, helping the patient that is using to certain things, like to localize better, to reduce the noise from the atmosphere or whatever acoustics in there embedded or whatever. And I see that this is going and going and going deeper and deeper. While there's another trend of saying, yeah, you know, we know that whatever you throw to the brain, they can deal with it, and the brain is very sophisticated. So I just wanted to hear your thoughts about where is this line. I see this robotic audition growing and growing in these devices and kind of taking over things that maybe the brain has to be doing. But we are putting a lot, we have the resources, we have new techniques, you have all the stuff you comment. So I don't know if you have any thoughts, if you push on pushing boundaries on there, or this robotic audition versus real brain fight, maybe in this.
Maybe I can, maybe I can start, and then Caleb can complete. But I think that the biggest challenge right now with hearing aids is that it's when you have what we referred to previously as the cocktail party effect. So if you are in a situation where many people are talking and you have this babble noise in the background, and you have a hard time understanding it, what your hearing aid will be doing is just amplify everything. And even if it's able to make it for some frequency region where you have a bad trouble hearing, the fact that it amplifies everything will be very annoying, very difficult to understand, and the brain is not able to process that. So many people with hearing aids would just turn it off when they are in a situation where a lot of people are talking. So I think in this case, the whole beamforming and the whole speaker listening to a specific person is very relevant. And I mean, I don't have any hearing issues, but to my understanding, by talking with people with hearing issues, this is something their brain is not able to adapt to when you have a lot of babble noise. So I think that's one way to tackle the issue, is to be able to improve the sound quality in that type of scenarios. Now, maybe Caleb has some further ideas.
I mean, I haven't worked with hearing aid as much. I mean, I've been approached by a lot of people because once I talk about Audition, they're like, "Oh, you, make me hear again, you." And what I believe is that usually when the brain reaches a certain limit, it provides a response, and it's usually an emotional one. Meaning that I would say that the line is where the discomfort comes in. Because like for example said, even without hearing aid, if I go to a dancing party with a lot of noise and a lot of that, even if I have a normal side of without having issues of hearing, I am discomforted with that. I mean, there's a lot of noise, I cannot hear anybody, etc., etc., etc. So that, I think that's where you can probably draw the line, not in terms of what the brain is able to do or not, because I mean, the brain is able to withstand torture. That doesn't mean that we should make the person go through torture because it could stand it. I think the issue here is what is a person capable of doing without bringing discomfort to that person. And I agree with you, Seba. I mean, it's a very difficult line to cross there, but I'm sorry, it's a very difficult line to put on there. And because the opposite of that is that maybe we're doing too much for the person and not let even when we're talking about little children that with the cochlear implants, we're not able to we're not letting them develop that part of the brain that is able to understand, that is able to adapt and learn from their cochlear implants. But yeah, I definitely agree with you. I'm sorry I don't have a better answer for that, but I think that the better way to go about it is that where is that discomfort? Where is that line of discomfort? Not in terms of what the brain is able to do or not. Is that where is that level of discomfort? And from there, just push down a bit. There's a comment from Usama, and I really want to address it. And says that just to add here, robot audition is not limited to source localization or speech classification, but more recent research tries to estimate the shape of room for effective robot navigation. Actually, that's not a recent thing. Well, a lot of robots in the beginning were using sound to do that. I mean, if we want to use sonar, that's one of is literally throwing sound at the environment and bringing it back. So the idea of using sound for these types of deals for obtaining the shape of the map of the space definitely is something that can be used. But it comes a little bit back to what we're talking about, because if you want to estimate the shape of room here, there are other type of modalities that are quite direct in doing that, laser or spatial vision. Again, I think we need to start, or I think we need to apply the modalities in which you see a direct correlation here. When we're talking about audio, it doesn't mean that with audio we're going to solve everything. Like, no, audio is a part of this deal, and we want to use that and complement what we're already doing. And although, to be fair, even though that it seems that I may be trashing the idea of using audio for room shapes, we should be doing that anyway, because the room of the shape it provides you a reverberation model that you then can use to remove reverberation from your audio. So I'm not knocking your idea, but we do need to find that bit of playing, like, what are we using for what purpose, and if it's the right tool for the job. But definitely that is something that has been done and should be continued to be doing.
People also use ultrasound to probe the room. So you just emit a signal and listen to the feedback. And also recently I've seen people using SLAM. So why not use a $5,000 LiDAR to scan the room? But yeah, these are things that you can do as well. And okay, so I guess
there are many others. There's another one from Tony. It says, have you explored the use of directional microphones for removing a layer of complexity? Ooh, that's a very good question, because usually a lot of the microphones that we end up using are omnidirectional ones.
You could have a directional microphone, say, on the head of the robot, so you just turn your head to the direction of sound and listen that direction. But I think the directional microphone, you can do a lot with omnidirectional microphone by just playing with the phase difference, and you get I would say a free directional microphone without any mechanical parts. So that's interesting. The slide that I don't know if you remember, it was a slide where I had these microphones all around the robots, and some pairs of microphones were not used because it was a closed array. So that's something I've used in the past, also for separation. So if someone is speaking on one side of the robot, I use only the microphones that are facing that person, and I just ignore the one behind the robot torso, and that improves by, say, 1 or 2 dB the separation. So you just drop microphones that are not relevant. So decrease the processing time and increase the quality. So that's because no microphones are fully omnidirectional. They always have some directionality.
Yeah.
So, yeah.
Actually, I was part of a service robotics group that we were doing exactly that. We were using omnidirectional microphones to know from where that user was talking, and then we use a directional microphone in his head to point toward that person. And even though the amount of noise was reduced considerably, there was a lot still of the presence of everything. So maybe a combination of those things can provide. Thank you, Joan. Am I saying their name correctly, Johannes or Juanes, or I don't know?
I think that's it.
I think it's Johannes.
Johannes. Okay. I'm gonna Mexicanize your name, man. So you're Juan now. Juan. So thank you a lot for your all of your questions, man. Or woman. I'm sorry. Juan or Johannes. Okay. Okay. So I'm gonna go in order of all the questions you established. Apart from the embeddings where each user has to be new class, can we introduce some taggings and reduce each user to n parameters that are the output of the network? Actually, that's very close to what embedding is. That's more or less what an embedding is. You're reducing this speech signal into this n to this n vector. So I'm not too sure what it will be the difference from each other, because the output of the network is, well, one of the networks is an embedding, and then we use it to compare to each other. Now, you could probably do a reduction of that embeddings domain in saying, like, instead of using 256 values, you can use 128. How representative will that be of your embedding space? It's up to the testing. But basically, you just defined, or maybe I'm not understanding your question correctly. But you're probably already there using an embedding in that sense. The embedding is fed to the main model to output user number, or am I missing something? Not exactly. The embedding is the thing that the network is outputting. So the idea is that you provide the audio directly to the network, and the output of the network is that embedding. Is a codification of your audio, and then you just compare those two with the other thing. Now you can use another network to compare those two. That's another, and that's what we were doing. But you can probably just use like a correlation measure or a cosine distance to do those two and see if those two embeddings are close to each other. But the idea is that the output of the network is the embedding.
Embedding is what you could compare to as a signature. Basically, you train a network and you have the last layer is the classification layer, and you can train a network with that. And then at the end, you just remove the classification layer and you check at the input that you were feeding to the classification network, and that becomes your embeddings. So basically extract the most relevant information about the user voice characteristics, and that is used for comparison purpose, like you compare with a dictionary and you see where's the best match. Okay. I think we can maybe move to the last question because time is running out. Did you use any psychoacoustic based compression? Is this indeed so far it's the input raw format, because if you eventually use that for, say, speech recognition, you have to be careful about what you do with the speech signal. Now you say, what about using inaudible information? Do you have to reduce the sampling frequency also? So if you want to go above 20 kilohertz, obviously you have to increase the FS, but you were thinking about using aliasing in purpose as a way to get a certain FS. That can be done, but be careful, however, because most codec, as you decrease the sample frequency, they have this internal FIR filter that will notch everything that goes above the Nyquist frequency, and some of them also have some analog filters that you don't really control. So I mean, that's something you can try. I've seen in the past we were able to capture some of the ultrasound in the the region where you hear something. This was definitely aliasing, but depending on the device you use, it can produce a whole bunch of very random behaviors. So that is definitely something you can do. I'm just saying be careful, because a lot of stuff is going with the codec, and they're doing some pre-filtering, which could be tricky. But yeah, it's not a bad idea. It's something you could do. But the easiest way is just to increase your sample rate and make sure that you don't have any aliasing. That's my advice.
In terms of the psychoacoustic-based compression, actually, there's a lot of features that have been used for a long while that was inspired by psychoacoustics. The Mel frequency substrate coefficients, where you were more or less modeled in a logarithmic type of deal in which the error works. Unfortunately with the MFCCs is that once you go to the MFCCs, you don't come back. So once you go that way, when you're talking to base compression, you need to come back from that if you're trying to do signal separation. But if you're doing classification, MFCC is still being used quite a lot for urban sound detection and even person detection. So definitely that is something that has been carried out. Now, in terms of what we're using directly from psychoacoustics, I'm not a psychologist. I don't think Francois is either. That's where we could probably use help from psychologists and psychiatrists and neurologists to inspire more types of techniques in that regard. But those two fields are not at all separated. There's a lot of there has been a lot of merging in terms of
and maybe one last comment is that there's always two different end goals. One end goal is to have the machine understand what's being said, right? So speech recognition, sound classification. The other end goal is to have someone listening to the process signal and have a human being able to better understand. And the thing is that these two end goals imply different methods. It's not because something sounds better to you that it will help the ASR system, and vice versa. So if you're designing a hearing aid system, or you're designing a codec or for a Zoom call, you might want to have some different cost function, like the PESQ score, for instance. Whereas if you're looking at ASR end goal, you will rather like focus on SDR metric, and also making sure that you don't introduce any nonlinear distortion that will break the speech recognizer. So I'm gonna
stop my screen sharing. Just I think you guys had enough of our faces in the.
I think that's pretty much we reached the 90 minutes period. But yeah, hopefully, Ioannis, that answers your
all your questions.
I hope
that was great.
Very good questions, by the way.
Very good
questions.
So
thank you for posting them.
Do you both need to run off now to lecture some students?
We'll have to run in maybe 5 to 10 minutes to get on the campus. But if there's anything else, I can answer
me too.
an extra 5 minutes, say.
Well, I just had one question about, we were speaking a little bit about hearing aids and hearing aid research. Do you get the impression that, I mean, are you guys really far ahead with this compared to what's actually integrated into hearing aids that are on the market, or do you not have an idea of that? Or is it the other way around, that those guys are
the amount of hearing aid that I've been, I mean, again, that's not my actual line of research, but I mean, I've been close to enough people to say that the high, those hearing aids that takes like $1,000, whatever. They're doing some stuff that are very, very interesting, but in my opinion, there's still some things that they can probably use in terms like direction simulation and separation and doing all that. But again, I understand why we're probably not doing that, because doing that requires a bunch of processing power that may not be able to be run in such a small space. But that's even the high line. When I'm talking about the moderate ones, if I understand correctly, and I'm willing to be instructed and to be corrected, is more or less more of the base, band frequencies and band filtering, et cetera, that you can probably maybe tune from somewhere, and even maybe in your phone, and then tune the thing over here, et cetera. But if I understand correctly, I mean, they're still in the audio signal processing part of it. I'm not too sure. I mean, I'm not too sure if that's the case, but from the colleagues and friends of mine that have been using moderate level types of hearing aid research, hearing aids, the amount of filtering that they're providing, the techniques that they're using are still, I mean, understandably low end. Now, again, I'm not wanting to knock here, because I understand it, because if you put this high end whatever, you'll need to put a backpack in your head for it to work. So that's, I think, even though that they're saying like if we're ahead or not, well, we're ahead in terms of dreaming, maybe. But even if I ask a person that hearing aids, they will say, "Oh yeah, we want to do that too." I mean, that's the goal, that's the dream. But the fact that we're able to do it, I mean, that may be the limiting factor, and that's where I think we can then start working together in that regard, and maybe inspiring each other to bring this in the forefront of maybe the idea that we're already there. We just limited by our
And
technology.
I also think that I mean, as soon as you want to take something and move it to the clinical side of things, it's a very complex process, and it should be complex because you want to have users, you want to have to go through like certification and all that. So I think there's the technical limitation, of course, like you have something like low cost, use very little power, and it's portable. And on top of that, you have the whole certification, make sure like people are comfortable with that. There's no long-term issues or thing like that. And we're just like engineers who like to play with stuff. But I'm fully aware that these guys have some more, like they have to make additional verification before introducing a new technology.
Yes. The medical, the safety part, the ethical part, probably also.
That's a big deal there.
Yeah. I see. Well, I think we better wrap it up. We've gone a little bit over time, but that was a really great presentation and nice that you presented together.
Yeah, well, thank you for inviting us. It was a pleasure to have a chance to talk about our research. Sometimes Caleb and I feel a bit isolated in our little research area because deep learning is so popular nowadays that we often forget that maybe there are some things that we have to do to make that usable, and this is where what we are interested in. So I think we will share the presentation as well after that. And please reach out to us if you have any other questions that you were maybe shy to ask here, or you didn't have time, or maybe these will pop later. But please don't hesitate. It's always a pleasure to talk about our research and exchange ideas at the same time. So
Excellent. Yeah, we'll share your contact info as well in the follow-up email.
Right.
So thanks a lot for joining us today, and we'll send out the email and a questionnaire if you have time to answer that as well. That'd be great. And stay tuned for our future webinars here at Danish Design Cluster.
So I'm gonna run to campus now.
Yeah, have a good day.
Teaching in 20 minutes.
Okay,
so thank you so much again, Shelley, for organizing all that. It was very appreciated. Thank you all for attending, and hopefully there will be a part 2 sometimes. Please don't hesitate to reach out.
Thank you very much, guys, for being here. Bye.
All right, take care. Have a great day.
You too. Bye.